This is a quick video over the sodium, potassium, ATPase. It's also known as the sodium potassium pump. Pump. So before we get started, let's say we're going to say our little green guy right here. He is sodium. He's a cation, and this little kind of big blue guy is actually potassium, and he is also a cation. The thing that you need to really know is that potassium is about 30% bigger. It's 30% bigger, and that size is really important because these both are positively charged ions. So the only way to tell the difference between them is for a cell is just the size difference. There's no way a cell can tell the difference. So if we were to randomly throw some of these up, just throw some sodiums around, just floating, and also some potassiums. And they were just randomly moving, all of them just randomly moving because it's at 25 degrees or 30 degrees Celsius. They're just randomly moving around. They're bumping into different things, all that. So they're just moving, and a couple may even move into this opening in our pump. This is the ATPase, or the sodium potassium ATPase, our pump. And when that happens, there's one really important thing to notice, is that the sodium can actually fit right here. Whoops, that's the color I was using. Can actually fit right here, here, and here. So once three things just randomly float in, something unique happens. A little thing on the side of the pump, about right here, allows for ATP to bind a phosphate group to it. So you have ATP come by, so ATP, and it turns into ADP. And when that occurs, a phosphate group is attached. The moment a phosphate group is attached, this whole thing wants to change shape. So you can kind of think of it as ATP providing energy. So it's just going to change its shape, and it's going to actually turn into this. And when this occurs, there's a conformational change, and we notice one really important thing, and that is that our sodium ions can't fit into these little holes anymore. So they just float out. Now something also important is, you see these other holes right here? The sodium ion is too small to stay in there, so they just randomly float on out. Just float on out. So after they have diffused on out, we can now see that a potassium ion can actually come floating by, and it actually fits perfectly into these. So our potassium ions can just diffuse on right into there. And the moment that the potassium ions diffuse into here, this phosphate group doesn't want to be there anymore. So it pops off and just becomes inorganic phosphate. So it just pops right on off. And the moment it doesn't have that phosphate group in here, it doesn't want to be in this shape anymore. It wants to convert back to its original shape, which was this. And when that occurs, our potassium ions, we had two of them, they can no longer fit into these little holes. They're much too big. They can't fit there, so they're forced out, they're squeezed out, and they just diffuse on out. And then the entire process can repeat itself, where then you have sodium ions come back and diffuse back into these little pockets that hold the sodium very well. Also, another important thing to note is that the sodium does not fit too well, or it fits in there, but it doesn't stay in there. The sodium is too small, so it might bounce in there, but it's not going to cause the shell pump to change or the protein to change in any shapes. It'll just go on there and bounce right back out. So it's all about the size difference between sodium and potassium. So let's just go over what happens. So when we do have this, we actually have the sodium diffuse in here connect, and the moment it connects, a phosphate group is attached. It turns into ADP. The ATP turns into ADP. So we have a transfer of three sodium ions. And here we have the transfer of 2 potassium ions. So here we have 2 potassium ions transferred across. So overall, we have ATP consumed, and it turns into ADP plus inorganic phosphate. We also have 3 sodium ions transferred from inside to the outside of the cell. Outside. And from the outside, we have, and that's different from that, from the outside, we have two potassium ions transferred from the outside to the inside. So overall, every time we use ATP, we get a positive charge across the membrane. So if there is a membrane here, the ATP never crosses the membrane, it's always inside. But if there is a membrane here, you would have the 3 sodiums pass and the 2 potassiums come across. So what happens is we actually get a slight positive charge on this side. Because we're taking 3 positive ions and moving them this way and only returning 2 positive ions. So we get a slight positive charge. And that's all I want to discuss about the sodium potassium pump, is that it's all about the differences in size of the sodium and potassium. Remember, the sodium will just randomly diffuse in. The potassium is too big to fit here or here, so it's forced out, so it doesn't want to go in there. But the sodium will fit in there nice and snugly. And the moment that these 3 sodium ions attach to this, that's when ATP is allowed to attach to this phosphate group. This phosphate group cannot attach until all of these 3 sodium ions are attached. And the moment we have, so we still have our phosphate group there, and the moment we have these two potassium spots filled, this phosphate group wants to pop off and become inorganic phosphate. And the moment this phosphate group pops off, it doesn't want to be in this shape anymore. It wants to convert back to its original shape, which is this. And that's the really important thing. It's this phosphate group that causes the change. And the only time it will ever be in this shape is when it doesn't have a phosphate group attached. When it has a phosphate group attached, it will be in this shape. So it's a phosphate group that causes the conformational change in the protein. And I guess that's all I have to say. Just remember, ATP is the energy source, and it provides the phosphate group.